In this interactivity, we're going to deal with Fleming's left-hand rule. Here's a piece of steel. The magnets have been fixed to provide a magnetic field from left to right. A conducting wire is passing in the middle. Let's deselect field lines to remove the lines of force and select vectors to show the flux density of a single vector arrow. Let's drag the current slider to the far left to allow the current to flow in the wire in a direction towards you. What happens to the wire? Yes, it moves upwards. You can see the vectors representing the force, which makes the wire moves upward. The flux density is represented as B and the current as I. Now let's select left-hand rule to display an image of a hand on the top of the three vector arrows. Place your left hand in the same direction as the one in the picture. You will see that, in this case, the thumb is in the motion direction, which is upwards. The first finger is in the field direction, which is from left to right, and the second finger is in the current direction towards you. This rule for finding the direction of the force in a conductor in a magnetic field is called Fleming's left-hand rule. Now let's deselect left-hand rule and try to change the direction of the current to see the effect on the direction of the force. So I will move the current slider to the far positive. What happens to the wire? Yes, you're right, it moves downwards. Now let's select the left-hand rule to see the direction. Place your left hand in the same direction as shown in the figure. So the thumb is in the motion direction downwards. First finger is in the field direction from left to right. The second finger is in the current direction away from you. Now, if we reverse the flux density, which is the field, notice how the vectors changes. So the motion thumb is now upwards. The first finger is in the field direction from right to left, and the second finger is in the current direction, which is away from you.